Well, thanks everybody for still being here, and thank you Compressor Tech 2 for having this great summit. This particular presentation happens to follow along with the article that Joel and I have in this month's issue of Compressor Tech, so you can take a look at that. I think the benefit of going last is that you get to take a look at which slides are repetitive, so I'll try to just zip past those. So we'll get started. So I think everybody kind of knows the different, what the rainbow of hydrogen is there, so go past that one. Source of hydrogen for recips, we've talked about steam methane reforming quite a bit. There's autothermal, partial oxidation, and electrolysis, so I think we've gone through that in pretty decent detail. So why use recips in hydrogen service? I think it's already been mentioned, they're relatively low cost and efficient for low to moderate flow rates, relatively speaking, relative to turbos. Easily handles high discharge pressures, up to about 3,000 PSI non-lube, but we can go higher than that at discharge pressures and good pressure ratios. Pretty well established metallurgy for hydrogen applications, H2 and hydrogen rich. But the real advantage is flow control flexibility. So where there's a real good differentiator here is that we can match the demand with minimal recycled flow. So there's all kinds of flow control devices, fixed step flow control, inlet valve unloaders, clearance pocket unloaders on the outer end, stepless flow control, infinite step systems, and we have a hydraulic VVCP, so you can automatically vary the outer end clearance. You can do manual VVCPs, and I think it was mentioned several times that some of the hydrogen storage applications are looking at frequent start-stops. So there's variable frequency drive that could be used for that kind of application. So pretty flexible. And I think this was talked about a couple of times, and the previous presentation kind of went through this, where recips and turbos fit. Everybody's got slightly different ideas, but pretty well agreed on recips being able to get to really high pressure ratios. That's not an issue. Can go up to very high pressures, but relatively lower flows, right, than turbos. So I think it's pretty well established. Hydrogen value chain, there's lots of nice diagrams on the value chain. With circles where recips fit in pretty well, so electrolysis on the far right, of course, refining applications, there's many of those. Hydrogen storage, that's up and coming. There are some hydrogen storage fields out there. There's going to be more. And then you could throw it in a pipeline, you could use it to power gas turbines. So recips have a good fit for those sorts of applications. So in hydrogen service, the traditional refining processes, I think, pretty well known: hydrocracking, hydrotreating, makeup and recycle gases. The makeups tend to be pretty, reasonably pure hydrogen. The recycles have other constituents, but are primarily hydrogen flare and vent gas recovery. This is the gas you don't want to get in the atmosphere. Hydrogen and hydrocarbon mixes typically often very sour. And then the other energy sectors been talked about: fuel for turbines, just blending. We've talked about blending, underground storage. That's going to be an up-and-comer, I think, and of course fuel cells. And then really interesting one is hydrotreating renewable diesel. I think that's a pretty cool application. Taking kind of solid waste or agricultural waste and making diesel out of it. So it's kind of neat. But so when we talk about compressor performance, really what is it? How do you define that? Well, technically, I guess you want to lower as low as possible brake horsepower per million, right? So that's one measure of efficiency: consumed power divided by the flow rate going through the machine. But the other aspect of that is reliability and availability. That can be measured by the amount of uptime, right? So you want to make sure the mean time between shutdowns is as long as possible. So with all that, the nominal topic here is about compressor valves. So lots of different types of valves in hydrogen service. These are just a few different geometries that we have: concentric rings, boarded plates, big poppets, some smaller poppet valves. So all the hydrogen that goes through the compressors goes through the valves. So we want to make sure that, the valves are often called the heart of the compressor. So we want to make sure that there's good heart health for our compressors, I guess. So a little bit of terminology. The gas flows through the inlet seat and out through the stop plate. So as goes the valve efficiency, so goes the compressor efficiency. The valve's not running, the compressor's not running. So we do everything we can to make sure we've got a good valve, so that it delivers the compressor delivers the flow of hydrogen with minimal power consumption. So just some definitions. A valve is basically a fancy orifice, right? So, and the flow area is defined by its geometry. So the different valve types I showed have different flow characteristics. We flow tested all those types of valves. And at the end of the day, you really want as much flow area as possible, and you want the flow path to be as aerodynamic as possible to minimize the valve pressure drop, because the lower the valve pressure drop, the lower the power consumption of the driver, and so you get better efficiency under those circumstances. So that's keeping the pressure drop to a minimum. When it comes to, there's another element of efficiency is the amount of fixed clearance in the valve. So the inlet stop plate and the discharge seat are adjacent to the cylinder bores, and they have an empty volume or clearance volume. So you want to minimize that amount of clearance volume because the more clearance there is in the valve, the less flow there's going to be through the machine. So we want to maximize flow area, but minimize fixed clearance through the valve. So the relationship to efficiency, we talked about the valve lift. Valve lift is nothing more than the vertical travel distance. It goes from open to closed position. So a higher lift provides more flow area. It opens up the area, but only up to a certain limit. We can test that. We can test those coefficients in the lab. Fortunately, with hydrogen, we can get away with the lower increments of lift and still be pretty efficient. So typical lift is 30 thousandths to 60 thousandths, where hydrogen is concerned. And valve pressure drop is proportional to the mole weight of the gas. And obviously the mole weight of the gas is as light as it can be at 2. So a pretty low valve pressure drop can be achieved in hydrogen service. So that's good. It's also good for reliability. This is just showing a quick chart on effective flow area. This is some flow testing that we did for the different types of valves. But again, kind of emphasizing the point that we want as much flow area with as little clearance volume as possible. This is just showing the flow area portion of the valve. A study was done back in 1995 on refinery compressors. So our company, when we were dresser end, went out and performed a study, asked our customers, what's the biggest reason for unscheduled compressor downtime on your recips? And by far, it was the compressor valves. So that's an obvious area to try to attack to improve reliability. Now that was back in 1995. Some people say it's still, that data hasn't changed much, but it kind of depends. Valve technology has improved quite a bit since then, so that chart isn't true for some people today, fortunately. Looking at, so getting away from efficiency a little bit, going to reliability, materials of construction and moving element design contribute to reliability. So materials, we think about gas compatibility, the strength of the materials, the impact resistance, corrosion resistance. Then on the moving element side, we look at the lift and the surface contact configuration, which turns out is very important. So the different materials, seat and stop plate, ductile liner, 17-4 stainless. For the moving elements, PEEK, polyether ether ketone, is kind of an industry standard. There's also some filled PTFEs, high strength PTFEs, but PEEK is well used. Spring, there's lots of different spring materials that work in hydrogen service very, very well. 7 pH stainless from silicon and other alloys. There's several good materials for hydrogen service. Moving element design. The forces acting on those moving elements are important to understand. So the differential pressure force, which is discharge minus inlet pressure, we provide a rating on the valve based on the differential pressure. So if you have a smaller, more robust element that has less tensile stress or less bending stress, then you should have higher reliability and a better rating, a higher pressure rating. The impact velocity force from the valve opening and closing events, those impose a pretty hefty force on the valve, so we want to minimize that. Fortunately, as I said, in hydrogen service, we can get away with low lifts, low valve lifts, keep the impact velocities to a minimum. So that's a good feature in hydrogen. We kind of like hydrogen because we can keep the lifts low and still keep the valve efficient. So, there. The moving element design, so this is pretty important. The strength of the moving element depends on the material and the geometry. So there's a bunch of different geometries for valves, but what we found over time is that the contact area, the nature of the contact area is really important. For ported plate valves and concentric ring type valves, that's basically flat contact. The poppet style valves had a more profiled edge, beveled contact, and that angled contact is able to withstand much, much higher impact velocities. So that's kind of what we use today. It disperses the energy quite a bit better. And here's some examples of those. So the big poppet element, the magnum and the hammerhead. So these are all PEEK materials. The magnum element, as you can see, if you look at the very top, the OD of each element towards the top, you can see there's a bevel there. So that those beveled surfaces provide good impact resistance, which is important. So the magnum is pretty small. It's kind of a bullet shaped. So we're able to use that at differential pressures about 3,000 psi or higher. The hammerhead to the right is kind of a takeoff, spin-off of the magnum. We can use that up to about 2,500 psi differential pressure. And again, this is with plastic, high-strength plastic. The poppet, on the other hand, which is an older design, maybe about 1,000 psi. And the reason for that is that you can kind of see there's a pretty good moment there. You know, it's a pretty big head diameter relative to the stem diameter. So there's a fairly decent moment that acts on that poppet, so it's much lower pressure rating. So I would say the state of the technology today is more magnum hammerhead kind of thing, at least for us. In years past, poppet valves were used quite a bit, only up to maybe the first or second stage though. So a lot of the makeup machines might be 2 or 3 stages typically. So in that third stage, it was a high enough differential pressure we couldn't use poppets, but with the magnum and hammerhead we can. So I think at this point I'm going to turn it over to Joel.
Good afternoon. All right. So we'll cover a little bit on the application of basically that magnum valve, that headless element valve, where it came from, where we put it. So as Steve mentioned, the different types of valves over the years, what we found was problems we had over the years with ring valves and plate valves and large poppet valves. We came up with this magnum valve element. So back in the mid to late 90s. And the whole point was to go up with one. He mentioned there's different valve types in different stages for different pressure ratios. So the goal of this was to really have one element that fixed almost all applications. So kind of the holy grail. Again, it uses the PEEK element. So we're going to look at a case study at a customer location, really, over a couple of decades. So before that, just to see, just for reference, so you can see where these types of valves have been installed over the years. You can see where the button is. Here we go. So this is really is mole weight versus discharge pressure. So you can see it's been used up to fairly high pressures, 5,000 pounds. You can see lines of mole weights. You kind of see the hydrogen applications, ethylene applications, CO2 applications. So, and the different colors are really just what we call high speed and low speed. So, there's high speed and compressors over 700 RPM. For your car, that's not even idling, right? So, if you like hot rods, it's not even warmed up. So just take a look at basically a refinery. This is repeated several times, but this one we have some information on the customer. I'll just take a look at this. So it's been, I get over 20 years. My hair was darker back then. So this customer had a fleet of 21 compressors, 50 cylinders in continuous operation. Their mean time between failure was about 10 months. So if you take averages, that was 16 valve failures per year. And they actually had a special crew of valve installation change-out crew, right? They just basically did it week after week after week. It was kind of, they just used to it. In the old days, that's the way it was. Everybody was changing valves out all the time. And then we started the first trial, one of those little headless valves, back in the late 90s. And he ran it for a few years in a couple of compressors, continuously for several years. Then he started filling up his fleet, basically changing them out as he got money to do it. And then you'll see from 2003 to 2007, a lot of the valves, or most of the valves were changed out to that type of valve, and the average number of failures per year went down to 2 valves. And that's in a refinery, so it's not pure hydrogen, but it's a lot of pure hydrogen, a lot of dirty hydrogen, I'll call it too. So they said in the panel there, hydrogen is not necessarily new for us, right? It's really nothing new for hydrogen other than pressures. In the added compressors, they continued changing out valves. I'd say by about that time they had almost every single compressor changed out. They're down to, they had an average failure of 1 valve per year. So that permanent valve crew basically lost their job, unfortunately. I'm sure they had other things to do. And then later on, they continued on with other applications. And the hammerhead valve that he showed is basically a pocket, right? Kind of a takeoff from the Magnum, as Steve mentioned. So he had over 500 valves in continuous operation. So the point there was the mean time between failure was basically 5 years. So you got several machines that run. Last one we talked was over 7 years. So that's a regular occurrence in hydrogen, not perfectly clean hydrogen either. So clean hydrogen really for recips, the good news is for the hydrogen business coming is it's not a problem. This is just a quick bar graph of that, looking at if you plotted percentage of valve failures per year, you can see a big drop off. So it really reduced the number down greatly. So that's good news for hydrogen, for compressors, for operators. So the old study from the 90s, which several people have probably seen over the years, but anyway, the point there was the valve is no longer the number one issue in recips. And that was always that way, pretty much. And again, like Steve was saying, that's the heart of the compressor, right? That thing cycles all the time, every day. And we're talking billions of cycles, right? So in your engineering school, everything was in vendors for seals. It's 10 million cycles is a long time, right? Well, that's just a couple of weeks in recip compressors. So in refineries, they want to run 3, 4, 5 years. Now they're talking 7 years, 8 years they want to run before they touch them. So and that's a quote from the customer here at this location. So concluding remarks, recip compressors are critical equipment for high pressure H2. Of course, it's not 10,000 pound. We do machines up to 10,000, but our hydrogen machines, most of them are less than 5,000 pounds in refineries. So recip compressors, again, we covered all that today several times, so I won't repeat it. But, again, efficient valves are important. Efficiency, again, is that cost of pumping the hydrogen or compressing it, right? So between unloading systems, variable unloading systems, and compressor valve efficiency, it's all important in hydrogen compressors. All right. Any questions?
I think we have time for one question, if anyone. I know, I think people want to get to the bar.
You're not all sleeping this
Oh, all right, here's one.
Well, almost got out of here.
Don't worry, it'll
Go
be
ahead.
quick. Have you gone back to that customer and asked to revalidate that curve or chart that you have?
Which one?
That one.
Yep.
So did they give you an actual value on the compressor valve failures? Like what's their main issue now? Is it pressure packing is it now, or is it still compressor valves?
Let's say a little louder.
Have you gone back to that customer and asked them to basically give you their mean time between failures and what their actual, major concern is nowadays? Is it pressure packing or is it still?
Oh, what's
compressor
moved
valve?
up the list?
I think it's the packing. It's
Basically,
the piston trim.
Basically, the next things in a row, yeah. Pressure packings, yeah.
Okay, thanks.
Packing rings. I mean, process conditions, obviously, a part of this is really, I always tell customers, you can make the stuff work or you can make it not work, right? So you gotta be involved. You can't just say, I'm gonna buy this, it's gonna run, all the problems go away. It's not true, right? So you've gotta be actively involved. So looking at the process. If you're a reliability engineer, refiner, you gotta look at the process, look at the gas, get involved in the chemistry and the process guys. It's a team effort, right? Along with the vendors. Again, the big thing is unplanned shutdowns. The big issue we had with that valve crew we had there, right, was really because of unplanned shutdowns. That's a killer in refineries. In gas plants, you can shut down, not that anybody wants to. It's not the end of the world. But refinery shuts down and you can't get back up quick enough. The dollars roll fast.
All right, thank you. Can we have a round of applause for